I'm going to derive Snell's law in this video, and if we take a look at like the basic refraction situation, you have light entering into a different material, and that angle of refraction, theta 2, I drew it here for some reason, it changes. And we're going to see, we're going to kind of derive like the relationship between the indices of refraction and these angles. And in order to do that, you kind of have to understand Fermat's principle. And what Fermat's principle tells us is that light will always take the path of shortest time between 2 points. So if you think about like these points right here, sorry for my mom's laughter, I don't know what amazing joke she heard. But if you have these 2 points right here and you're trying to figure out all the different paths light can take, you know, it can take all sorts of paths. It can go straight down and into that point. It can go like this, right? There's all sorts of paths. Oh my God, this is all the way over here. There's all sorts of paths light can take. And we need to find the path that would minimize the time. So we need to get essentially an equation for the time it takes for light to hit this point based off the angles and the distances and stuff, and then we can use calculus to minimize it. So suppose there is a path of shortest time, right? Well, for this, or I guess for any path, you can imagine creating some right triangles. You can imagine creating a right triangle like so, and a right triangle like so. So for this right triangle, for the top right triangle, it can have maybe a distance x and a height h above the line of the chain of medium. And for here, if the total distance we could say is a, right? Then for a minus x is going to be the distance. And what we're going to do, this is probably not the most rigorous thing to do as in terms of a proof, but just so that we, one, simplify the problem, and two, just understand the intuition behind this, we're going to say that the path of shortest time is going to be like within a, right? Like a we can treat as a constant. It's not going to be a changing distance, because if you go past a, right, there's no way it's going to be the path of shortest time because these distances are way long. And maybe you could prove that that is the case, but we don't need to do a rigorous proof. Just know that a we can treat as a constant. So a, whatever path light takes, we're going to say it's within a in terms of what is the path of shortest time. So a minus x would be this leg of the right triangle, not light triangle, but I guess it is a right triangle or light triangle. And then we'll call this height y. So the time it takes is going to be pretty simple. So the time it takes, t, will equal, by Pythagorean theorem, this side is square root x squared plus h squared. So root x squared plus h squared over the speed of light, which we could say v1. And we'll relate that back to the index of refraction, because v ends up being c over n. And we're going to add on to that, right? That's the time it takes for this first segment. In the second segment, it's going to be square root a minus x squared plus y squared over v2. Now we can just minimize this time by finding the derivative and setting it equal to 0. So dt, we're going to take the derivative with respect to x. That's going to be the changing variable here, right? Because for all of these paths, h is a constant, y is a constant. But the main thing that it's changing is this x, how much the light travels horizontally before it changes mediums. So dt over dx, v1 is a constant, so v1 is a constant, so we can pull that out of the derivative. For the derivative of the top, we can use chain rule, right? So the square root, the derivative of a square root is going to be 1 over 2 times root x squared plus h squared, or whatever's inside that root. And then we're going to multiply it by the derivative of the inside of that root, which is going to be 2x, because h is a constant, right? The height from the initial point to the line where mediums change, that's just going to be a constant, right? This height doesn't change. It's just a horizontal distance. And now we're going to add on to this the derivative of this, right? So dt over dx. Wait, what am I doing? I'm in my head. I was thinking that you're going to do d over dx here, d over dx here. So I just wrote that out. But d over dx for this, we can pull out the 1 over v2 times 1 times this, 1 over 2 root a minus x squared plus y squared times derivative of the inner. Now we're going to have to do like a chain rule twice, right? Because the derivative of the inside, well, you have that a minus x squared. So it's going to equal 2 times a minus x. And then you finally do the derivative of what's inside here, which is just negative 1. So this we can just change to a negative. And we know when we're minimizing time, the derivative is going to equal 0. So we can essentially, first of all, drop these 2's, right? Because they cancel for both these fractions. We're going to add it over to both sides because this ends up being 0. So you essentially get x over v1 times square root x squared plus h squared is going to equal a minus x over v2 square root a minus x squared plus y squared. So what we see now is that, well, v1, right, we know that the speed of light in any material is going to equal the speed of light in a vacuum over the index of refraction. So in that case, 1 over v is just n over c when you take the reciprocal. So we can just replace these 1 over v1s with n1 times x over c square root x squared plus h squared is an equal n2 over c times a minus x. Sorry for my mom's chatter, she's on call with someone. N2 over c times square root a minus x squared plus y squared. The c's drop, right, because they're both constants. It's just speed of light in a vacuum. And maybe you can kind of see where this is going. X over square root x squared plus h squared, that is just sine theta 1, right? This distance is square root x squared plus h squared. So the sine of this angle is the opposite x over that square root. So n1 times sine theta 1. We can replace that this whole x over square root x squared plus h squared with sine theta 1. And similarly, you can probably see now, you can do the same thing with the fraction on this side, right? The a minus x over square root a minus x squared plus y squared. That's just sine theta 2. Because this distance right here is a minus x squared plus y squared. So this ends up being sine theta 2, the a minus x over the distance. So this is Snell's law right here. Clear as day. It just comes from minimizing the time. It just comes from Fermat's principle. It's a numerical way, I guess, to express Fermat's principle. So yeah, pretty cool derivation. Hopefully the steps kind of made sense, even if you kind of got lost in the sauce of the calculus, because you don't really need to know this for AP Physics 2. But yeah, hopefully that kind of made sense.